So in this video, let's have components of a force resolution. So you should undergo with this so that you will be prepared for another technique on finding the resultant of coplanar concurrent force systems in 2D space. And I hope that the techniques here will help you improve in your analysis. So for the rectangular components of a force, we define first force resolution as the process of expressing a force into its components. So it is like given the resultant to find the components of the resultant, or given the main diagonal of the parallelogram to find the other sides of the parallelogram. So of course you have to use law of sines here, or law of cosines. Then it will be purely trigonometry. For the general case, if you have a parallelogram, use the law of sines or cosines to find the components or the other sides of the triangle. For a special case, it reduces to a rectangle, so use trigonometric functions. So SOHCAHTOA for right triangles with the notion of sine of the components. So remember that these components may be positive or negative. Positive in the direction of the established axis. Negative if it is opposite to the established axis. So standard position of an angle, there are situations where the forces are placed on an specified x and y axis. So these are the possible position of the resultant or force. Then remember that the standard position of an angle is counterclockwise from the positive x-axis. So in this case, we have theta here. Then this is theta from the positive axis to the line of action of R. The advantage with this is you don't need to think about the sign. It will give us the correct signs immediately. Then for a force or resultant in the third quadrant, that should be the standard angle, standard position or standard measurement of the angle theta in counterclockwise direction. Then if it is in the fourth quadrant, that's the established theta. If you use the angle in clockwise direction, then you can. However, you make it negative. So for example, if this angle measurement is 320 degrees positive in counterclockwise direction, then this should be negative 40 degrees. So you can use negative 40. So the formula should be for Rx, it is R cosine theta. You don't think of the sign anymore. It will automatically give us the correct signs. Ry is R sine theta if the theta is in this standard measurement. Then we don't think about the sign of the components. If you use the reference angle, remember reference angle is an acute angle between the x-axis, positive or negative x-axis, and the terminal side of the force. So if it is in the first quadrant, then this is the reference angle, and Rx is plus minus R cosine theta in general. Ry is also plus minus R sine of theta R. Then for the sine, it's up to you. You look at the direction of the force. So if it is in the first quadrant, if the resultant force is in the first quadrant, then both Rx and Ry must be positive. If R lies in the second quadrant, Rx is negative and Ry is positive. If it lies in the third, both x and y components are negative. If it lies in the third, rather. If it lies in the fourth quadrant, only the x component is positive, the y component is negative. So that's it. Always remember this, it's just trigonometry. Now, what if we have the general case, components of a force with respect to u and v axis. So in general, if u and v axis are not perpendicular to each other, then the technique is from the tip of the force or resultant force, you draw lines parallel to this set of axes so that you can form a parallelogram like that. So this is Fu and that is Fv. So in this case, because Fu and Fv are in the positive directions of u and v axis respectively, these components will be positive. So next, if we have u and v axis, so the technique is again we draw lines parallel to these sets of axes through the tips of the resultant. Then notice that Fu is negative because it is in the negative direction of the u-axis, while Fv remains positive. Then the third case is when both the u and the v-axis are negative. The u and v components are negative. So same technique, you draw lines through the tip of the force parallel to this set of axes. Then this is Fu, which is negative, expected negative because it is in the opposite direction of u. And this is Fv, which is also opposite in the direction of v, so it's also negative. Now, use law of sines to compute these components. So you can analyze the angles. That's not a problem anymore because you'll be the one to analyze that. You can find the angles. So I'll call this angle lambda. This one as lambda, same, lambda. And the angle here as P, opposite to Fu, P, then P. Then apply law of sines. R as to sine lambda equals Fu as to sine P equals Fv as to sine of theta plus alpha or sine of alpha plus theta. Then in this situation, we have R as to sine of lambda equals negative Fu as to sine of P because Fu is negative equals Fv as to sine of quantity theta plus alpha. In this third case, R as to sine of gamma rather equals negative Fu as to sine of P equals negative Fv as to sine of quantity theta plus alpha. So this is gamma. Gamma. Sorry, I misnamed it. So that's it. So let's have a new topic. It's called early vectors because this is important in gaining another technique in resolving a force into its components. And in order for you to be prepared for 3D system in the future videos. So vector expressions will be introduced here for 2D cases to prepare you to the general vector representations of a force in the succeeding videos. A vector is represented by the following ways. One is we have a vector A with arrowhead on top, then equals AXI plus AYJ, or boldface symbol for vector, then AXI plus AYJ, where AX and AY are the X and Y components of the vector, and I and J are the unit vectors along X and Y axis. One important operation of vectors is the dot product, and it is A dot B equals magnitude of A, magnitude of B, cosine of the angle between them, theta. So the application should be to determine the component of one vector in the direction of the other vector, or the component of the other vector in the direction of the first vector. And the other thing is we can solve or determine the angle between the two vectors. So those are the applications of the dot product. So for instance, we have vector A here, vector B. So to determine the component of A in the direction of B, all you have to do is from the tip of A, we project a line perpendicular to B, and we can form a right triangle. Therefore, this component is A cosine of this angle here, which I denoted, which we will denote theta. So that's A cosine theta. Likewise, if we project a line from the tip of B
down to the vector A or perpendicular to A, then this component is the component of B in the direction of A, which is B cosine theta. And because this is the angle theta. So A cosine theta therefore is equal to A dot vector B divided by magnitude of B, and this is taken from this formula here because A cosine of theta is A dot B divided by B. Okay? A dot B divided by B. And the ratio of vector B to its magnitude is the unit vector B. So A cosine of theta equals A dot lambda of B. Likewise, B cosine theta is equal to A dot B divided by A, or A over vector A over magnitude of A dot B. Because that product is commutative, instead of writing this as lambda of A dot B, it can also be expressed as B dot lambda of A. Again, vector dot product is, or that product is commutative. And that product is scalar, by the way. So that product is commutative as result. So I dot I is 1 times 1 cosine of 0 degree. So that is 1 because the angle between unit vector I and another unit vector I is 0. And the magnitude of unit vector I is 1. So 1 times the cosine of the angle between them is 1. Similarly, j dot j is also 1. 1 times 1 cosine of 0, that's 1. While I dot j is j dot I equals 1 times the cosine of the angle between I and j, or j and I, is 90 degrees. Therefore, it is 0. So cosine of 90 is 0. So A dot B, therefore, in terms of components, is AXI plus AYJ dot quantity BXI plus BYJ. And we perform multiplication, distributive law of multiplication over addition. So we have AX BX I dot I plus AX BY I dot J plus AY BX J dot I plus AY BY J dot J. And remember that I dot I is 1, I dot J is 0, J dot I is 0, and J dot J is 1. Therefore, A dot B is simply AX BX plus AY BY. Or simply, the dot product between two vectors is simply the sum of the product of corresponding components. So that's the result, sum of product of corresponding components. So if the force F has a magnitude of F and directed theta counterclockwise, theta degrees counterclockwise from the positive x-axis, then its vector representation is F is boldface F equals magnitude of F dot, or F is boldface F or vector F dot lambda of F, or simply F magnitude of F quantity cosine of theta I plus sine theta j, because the angle that F makes with the positive x-axis is in general theta. And remember, F cosine theta is the x component of the vector or the force, and F sine theta is the y component of the force. And remember also that the unit vector cosine theta I plus sine theta j has a magnitude of 1 because remember, square root of cosine squared theta plus sine squared theta, that's an identity. That's 1. Square root of 1 is 1. So that's it.
Let me emphasize that for vector approach, Fu is the dot product of F and the unit vector of the u-axis, and Fv is the dot product between F and the unit vector for the v-axis. And this is applicable, very important, only when u and v are perpendicular to each other. So this is not applicable when u and v are not perpendicular to each other. So I have two examples for the applications of this. But the best way is the previous technique, which is you draw a parallelogram, then just apply law of sines and law of cosines and think of the sign of the components Fu and Fv. So let me emphasize that u and v axis must be perpendicular, or else we cannot apply this. So level 1 problem, determine the horizontal and vertical components of each force shown below. So we have three forces here. So this is level 1, very simple. So from the figure, F horizontal is going to the right, so rightward component, and it is equal to hypotenuse, which is F cosine of 48. So FH is 12 cosine 48. So FH is 8.030 kilonewtons rightward. FV is also upward. This component here, it is opposite of 48, so it is hypotenuse sine of 48. So 12 sine of 48 degrees. And it is upward, 8.918 kilonewtons upward. For the second force, the hypotenuse here, remember proportions of right triangle, 3, 4, so this is 5. The x component is leftward and it is hypotenuse 180. X component of distance divided by hypotenuse. So P sub h is 180 times 3 over 5. pH equals 108.0 newtons leftward. You may not show leftward, but you have to put a sign negative if you want. P sub v is upward, so it is 180 times 4 over 5. So P sub v is 144.0 newtons upward. Then for the third force, Q is directed leftward and downward. So supposedly they are negative, but you can make them positive as long as you show the arrow direction. So 5, 12, so the hypotenuse is 13. Q sub h is equal to 520 times x component of distance 5 over hypotenuse 13. So 520 times 5 over 13, so QH is 200 newtons leftward. Then finally Q sub V is 520 times 12 over 13. So QH is equal to 480 newtons downward. Level 2 problem. Determine the horizontal and vertical components of each vector shown below. So the first vector is a force, second vector is velocity, third vector is acceleration. So these are vectors with components, and the components may be positive or negative. For the first one, it is directed down to the right, so rightward for the horizontal, downward for the vertical. So familiar with the proportion 7 to the 4, so the hypotenuse is 25. Therefore, T horizontal is 2000 times 7 over 25 rightward. So T horizontal is equal to 560 newtons rightward. Then T vertical is 2000 times 24 over 25. So T vertical is 1920 newtons downward. V horizontal is opposite to 52, so it is 75 sine of 52. And it is leftward. So V horizontal is 59.10 kilometers per hour leftward. V vertical is upward. It is adjacent, so 75 cosine of 52. V vertical. So it is equal to 46.17 kilometers per hour. Then third acceleration, it is down to the left. So leftward for horizontal, downward for vertical. So A horizontal, so 8, 15, so this must be 17, the hypotenuse. A horizontal is 6.75 times 8 over 17, leftward. So A horizontal is 3.176 meters per second square, leftward. A vertical is downward, 6.75 times 15 over 17. So A vertical is equal to 5.956 meters per second square downward. Level 3 problem, resolve each of the four shown below into x and y components. So this is still an easy problem. 960 is directed up to the left, so the x component is leftward or negative. The y component is positive. So the x horizontal component is px, and it is 960 cosine of 56 degrees 42 minutes. And because it is leftward, you anticipate that it is negative. So px is negative 527.1 newtons because we have axis x and y. Before, there was no x and y axis, so that's why we have to indicate if it is leftward, upward, downward, or rightward. Here, it is obvious that it is in the second quadrant, so the x component is negative, the y component is positive. So py is 960 sine 56 degrees 42 minutes, it is positive. So py is 802.4 newtons. Fx is negative to the left, so it is 58.85. This is Fx, it is opposite to 63.4, so it is negative 58.85 sine of 63.4 degrees. So Fx is negative 52.62. Fy is downward and it is adjacent to 63 degrees, 63.4 degrees. So it is also negative 58.85 cosine of 63.4 degrees. So Fy is negative 26.38 kilonewtons. Level 4 problem. Resolve the force shown below into x and y components by transforming the angle into standard value. Check the components using the reference angle. So another technique, the one that we will not think anymore of the sign, the automatic, but we have to determine the standard angle value. So this is 32 degrees. So from the positive x-axis, 90 plus 32, the standard theta for that force is 90 plus 32, so 122 degrees. So therefore, we expect that x component is negative, y component is positive. So px is 270 cosine of 122. So P sub x is negative 143.1 newtons. P sub y is 270 sine of 122. By the way, let's check first if it is negative 140.1. The reference angle is 90 degrees minus 32 because that's 90 here. So my 90 degrees minus 32, the reference angle is 58. The angle, acute angle between the terminal side of the force and the x-axis, positive or negative. So therefore, because px 270 is directed to the left, it is negative 270 cosine of 58. So you have to anticipate the sign. So px is negative 140.1, which is the same as this. Py is upward, so it is 270 sine of 58. 270 sine of 122 for the standard angle. So Py is 229.0 newtons. For the reference angle, it is expected positive, so 270, positive 270 sine of 58. The reference angle is 58 degrees. So P sub y is also 229.0 newtons. Level 5, resolve the force shown below into x and y components by transforming the angle into standard value. Check the components using the reference angle. So here is the force. For the solution, the angle would be 90, 180, 270 plus 50. So therefore, the standard angle for this force is 320 degrees. So Px is 75 cosine of 320. Without thinking of the sign, it will automatically give us positive value because it is in the fourth quadrant. Obviously, Fx is positive. Then for the y component, for the other technique, if you use this angle, it should be clockwise, so it is negative 40. The reference angle is positive 40, but in standard form, if you measure it in clockwise direction, negative 40. So another way of computing Fx is 75 cosine of negative 40. 75 cosine of negative 40, and it is still positive 57.45 kilonewtons. Using the reference angle, it is positive 40. Fx is going to the right, so it is 75 cosine of 40 positive using the reference angle. Then for the y component, using 320 degrees, it is 75 sine of 320. So Py is negative 48.21. If you use the 40 degrees clockwise, it is 75 sine of negative 40. Fy is also 75 sine of negative 40. So Py is negative 48.21 kilonewtons. Then if you use the reference angle, Py is, because it is going down, negative 75 sine of 40. So Py is negative 48.21 kilonewtons. Level 6, resolve the force shown below into U and V components into two ways. So the other way would be the vector approach. Fu is F dot lambda of U. Then Fv, F lambda of V, unit vector of V. So let's superimpose the force here so that we can analyze the angle. So this is now the force. So from the tip of the force, first technique, we draw lines parallel to the U and the V axis to form a parallelogram which is reduced to a rectangle because U and V are perpendicular to each other. So this is 90 because that's also 20. So perpendicular to each other, that's why we can use the vector approach. So therefore, this is 60 minus 20, so this angle is 40 degrees. And this is the Fu component, which is positive, and Fv component, which is also positive. So in this right triangle, Fu is 200 cosine of 40, while Fv opposite to 40 is 200 sine of 40. So Fu is 200 cosine of 40 degrees. So Fu is 153.2 newtons, and it is directed up to the right 20 degrees. But if it is in the drawing, you may not introduce it because it is already in the drawing. There are situations where you have to report in this manner because remember these forces are vector quantities, so it must have directions, although it's obvious in the figure. Then Fv is 200 sine of 40. So Fv is 128.6 newtons directed because this is 20 degrees, this is 70 degrees up to the left, 70 degrees. Then for the vector approach, F is magnitude of the force in vector form, quantity cosine of 60 because it forms an angle of 60, standard position, I plus sine 60 degrees J. So the vector representation of the force is its magnitude, quantity, unit vector of its direction, which is cosine of 60 degrees I plus sine 60 degrees J. So remember that this is lambda or unit vector of F. So simplifying, 200 cosine 60 is 100 I plus 200 sine 60, 173.2 J. Then the unit vector of U, because it forms an angle of 20 degrees, it is just cosine of 20i plus sine of 620 degrees J. Cosine of 20 degrees I plus sine 20 degrees J. Then the component Fu is the dot product of F and lambda of U. And remember that I dot I is 1, I dot J is 0, J dot I is 0, and J dot J is 1. So you only multiply 100 cosine 20 and 173.2 sine of 20. So 100 cosine of 20 degrees plus 173.2 sine of 20 degrees. Remember that product. So Fu will give us 153.2, same angle. The unit vector of the v-axis is, because this is already 90 plus 20, 110 degrees. So the unit vector of v is quantity cosine of 110 degrees I plus sine 110 degrees J. 110 is from the x-axis 90 plus 20 additional, so 110. Then FV is quantity 100 I plus 173.2 J dot cosine of 110 degrees I sine 110 degrees J. So it is 100 cosine 110, you just use your calculator there, plus 173.2 times sine 110. So the value of FV is the same as that, 128.6, then directed up to the left, theta 70 degrees. Level 7, resolve the force shown below into U and V components into two ways. So let's superimpose the 60 kilonewton load. So we have this measurement of angle. Then the angle that P makes with the horizontal, this axis here, is equal to this angle. So tangent of theta of B is 3 over 4. So inverse tangent of 3 over 4 is 36.87 degrees. So since this is 20, this angle therefore is 36.87 minus 20, so 16.87. So from the tip of the force P, we draw lines parallel to the U and the V axis, parallel to V and parallel to U, so that we can form this rectangle. So this is PU, which is negative, PV also negative, because they are in the opposite directions. Both are negative components. So that's it. And the measure of this angle is 36.87 minus 20, so 16.87. So therefore, PU is negative 60 cosine of 16.87. So negative 60 cosine of 16.87, we anticipate it. So P sub U is negative 57.42 kilonewtons. While P sub V is also negative, it is opposite, so 60 sine of 16.87. Negative 60 sine of 16.87. So P sub V is negative 17.41 kilonewtons. For the vector approach, P, the angle from the positive x-axis is 180 up to here, plus 36.87. 180 plus 36.87 is 216.87. Therefore, in vector form, P is 60 quantity cosine of 216.87, 180 plus 36.87 plus cosine of 216.87i plus sine of 216.87j. So 60 quantity cosine of 216.87 degrees I plus sine 216.87j. So simplifying, P is negative 48i minus 36j. While the unit vector of U is the same, cosine of 20 degrees I plus sine of 20 degrees j. While the unit vector of V is, lambda of V is cosine 110 degrees I plus sine 110 degrees j. Same as before. So therefore, lambda of U, PU is P dot lambda of U. So PU is P dot lambda of U, PV is P dot lambda of V, unit vector. So PU is quantity negative 48i minus 36j dot with quantity cosine 20 degrees I sine 20 degrees j. That is applicable as long as the U and V axes are perpendicular. So it is negative 48 cosine 20 minus 36 sine of 20. So PU is negative 48 cosine 20 degrees minus 36 sine of 20 degrees. So P sub U is the same, negative 57.42 kilonewtons, while P sub V is quantity negative 48I minus 36J dot quantity cosine 110 degrees I plus sine 110 degrees J. So you just use your calculator there. We run out of space. Negative 48 cosine 110 degrees, then negative 36 sine 110 degrees. So P sub V is negative 17.41 kilonewtons. Level 8 problem. This is the last problem for the basic part. A crate is pushed up a slope by a force of 160 newtons. Find the component parallel to the slope and the component perpendicular to the slope. So here is the given figure. Solution. So this is 20 degrees. Then let's draw it here. Let's superimpose the force and the tangential and the normal axis. So this is 160. Then this is 20 degrees. The inclined plane makes an angle of 20 degrees with the horizontal. This is the inclined, then this is horizontal. So that's 20 degrees. So that angle that the 160 Newton force makes with the tangential axis is 12 plus 20 or 32 degrees. And these are the components. Ft, which is in the direction, positive direction, so positive Ft, while Fn is in the opposite direction, going down, because the force is down, then in the direction of t. So Ft is positive, Fn is negative. What is Ft? It is 160, because this is a right triangle. It is 160, then adjacent to 32 degrees or 12 plus 20. So 160 cosine of 12 plus 20. 12 degrees plus 20 degrees. So F sub t is positive 135.7 newtons. While Fn is negative, opposite to 12 and 20. So it is 100, negative 160 sine of quantity 12 degrees plus 20. So Fn is equal to negative 84.79 newtons. Level 9 problem. This is the start of moderate problems. A person on a swing seat is pushed by a 250 Newton force at the position shown in the figure. Determine the component parallel and perpendicular to the swing chain. So here is the given figure. The angle between this normal and the vertical is 30, and the angle of the force inclined is 18 degrees only. So the we can analyze for the angle that the force makes with the line perpendicular to the swing chain and parallel to the swing chain. So this is 18 degrees from the horizontal, and we expect that the tangential axis should be, or the angle of inclination for the tangential axis should be 30 degrees. But this is only 18 degrees, so therefore this is 30 minus 18, so 12 degrees. Then this is f sub t, so it is positive. The normal component or along the normal plane is negative, and we have a right triangle here. So ft is adjacent to 12 degrees, so it is positive 250 cosine of 12, while fn is opposite and it is negative, so it is negative 250 sine of 12. So ft is positive 250 cosine of 12 degrees, so it is 244.5 newtons, while Fn is negative, so it is negative 250 sine opposite this one, sine of 12. Negative 250 sine of 12 degrees. So Fn is negative 51.98 newtons. For level 10 problem, in level flight, the chord AB of an airplane wing makes an angle of 5 degrees. Alpha is 5 degrees with the horizontal. The resultant wind pressure on the wing for such conditions is defined by its lift and drag. Lift and drag components, L is 7,500 newtons and the drag force is 1,000 newtons, which are vertical and horizontal respectively as shown in the figure. Resolve this force into rectangular components T and N coinciding with the chord AB and its normal respectively. So this is the airfoil, and this is the tangential axis along chord AB, then normal perpendicular to tangential axis. That's why we have alpha here and same angle alpha, which is 5 degrees. So the technique is, because we have two forces, we have to find the resultant first between this drag force and lift force. Luckily, they are perpendicular, so it's easy to compute for the resultant. So draw lines from their tips to form this rectangle. Then this is the resultant, F. Let's call that F. Then the magnitude of F is square root of 1,000 square drag force plus lift force square, 7,500. And then for the tangential and normal components from the tip of that resultant, we draw lines parallel to the normal, which is this blue here, and parallel to the tangential, which is this one, which is also that one. So both the tangential and the normal components are positive in this case. But we have to solve for the magnitude of F first. So this is Ft and that is Fn. That's why they are both positive. And let's call this angle between F and the vertical as beta. Angle between the force F and the vertical as beta. So R is square root of 1,000 square plus 7,500 square. So the magnitude is 7,566 newtons. Then tangent of beta is opposite, which is drag force over adjacent, the lift force. Tangent theta is 1,000 over 7,500. Therefore, beta is 7.595 degrees, which is greater than alpha because alpha is only 5 degrees. Therefore, from this right triangle between Fn and F, that's a right triangle there, the angle here is 7.595 degrees minus 5 degrees. So that's 2.595. So Fn therefore is F, 756 F or R. Uh, let's call this R. So it is 7566 cosine of quantity 7.595 degrees minus 5 degrees for Fn. For Ft, it is opposite, so 7566 sine of quantity 7.595 minus 5 degrees. So ft is 7566 sine of this one. This is the sine of 7.595 degrees minus 5 degrees. So it is 342.6 newtons, while F normal is 7566 cosine of 7.595 degrees minus 5 degrees. So F normal is equal to 7558 newtons. So this is F, not R. Level 11 problem. For the position shown, the connecting rod BA of an engine exerts a force F of 2,500 newtons on the crank pin at A. Resolve this force into rectangular components, horizontal and vertical, at A. So here is the given figure to find the horizontal and vertical components of F. So we must find this angle here, which is also the angle that F makes with the horizontal. So I'll call that theta. That is also theta. Then to solve for theta, let's deal with this triangle here by sine law. 500 as to sine 45 degrees equals 250 as to sine theta. So theta is 20.7 degrees. Therefore, FH is F cosine of theta, and it is rightward. So 250 cosine of 2500 cosine of 20.7 degrees. So FH is 2339 newtons rightward. While FV is going down, so it is F 2500 opposite to theta, so sine of 20.7 degrees. So FV is 883.7 newtons downward. Level 12. The control rod AP exerts a force F on the sector as shown. Determine both the X and Y and the normal and tangential components of the force. So here is the given figure or the solution. So this is the X and this is the Y axis. So considering the X and the Y axis, we draw horizontal line parallel to X and vertical line parallel to Y. So Fx is going to the left, Fy is going down. So both Fx and Fy are negative, and the angle is beta, and Fx is opposite to beta. So Fx is negative F sine of beta, or yes, negative F sine of beta, or leftward, F sine beta leftward. So for the normal and tangential component, we draw a line perpendicular to this inclined plane here, which is making an angle of alpha. So remember the principle, the angle of inclination, alpha, is also the angle between the vertical and the normal. So this is also alpha. So again, for Fx, it is this one, negative, or it is F sine of beta, leftward, but if you don't indicate the direction, it is negative F sine beta. Fy is in this direction also, going down. That is Fx, this is Fy, and this is also Fy adjacent to beta. So Fy is F cosine of beta, downward, or simply Fy is negative F cosine of beta. For the tangential and normal components, we draw lines parallel to the normal and tangential through the tips of F, which is here. So we form this rectangle. This angle is alpha plus beta, and this is Fn, which is in the direction of positive direction of the normal. And this is Ft, which is equal to this, also in the direction of the tangential axis. So both are positive. For Ft, which is this, adjacent to alpha and beta, so it is F cosine of alpha plus beta. So that's Fn, and this is Ft, which is also equal to this. So again, Fn is in the positive directions, and it is opposite to alpha and beta. So Fn is f sine of quantity alpha plus beta, while Ft adjacent to alpha and beta is f cosine of quantity alpha plus beta. That's Ft. Fn opposite to alpha and beta, so it is f sine of alpha plus beta. Both are positive because they are in the direction of the normal and the tangential axis. So that's it for this problem. Level 13. The T component of the force F is known to be 150 newtons. Determine the N component and the magnitude of F. So here is the given figure. So let's draw lines parallel to T and N axis through the F, through the tip. So imagine this is the tip of the force. So we draw lines parallel to normal and parallel to the tangential axis. So this is now the rectangle because the tangential axis and the normal axis are perpendicular to each other. So if this angle is 30, this is also 30 degrees here. So the total angle that F makes with the incline or the T axis is 40 degrees, 10 plus 30. Fn is in the opposite direction because the positive direction of the normal axis is going up. It is opposite, so negative. Ft is in the same direction, so therefore Ft is positive. That's why its magnitude is 150. And it is F cosine, because this is adjacent to 10 plus 30. Cosine of 10 plus 30, it is equated to 150, so we can compute the magnitude of F. So that's Ft and Fn. Ft is positive, Fn is negative. So Ft is F cosine of 10 degrees plus 30 degrees, this angle here, and it is equal to 150. So F therefore is 150 cosine of 40. So the magnitude of F is 195.8 newtons. Having found F, Fn is expected negative, it is opposite to 10 plus 30 degrees, so it is F negative F sine of 10 plus 30 degrees. Negative 195.8 sine of 10 degrees plus 30 degrees. So it is negative 125.9 newtons. That's it for this problem. Level 14, determine the scalar components R sub A and R sub B of the force R along the non-rectangular axis A and B. So this time the axis A and B are not perpendicular to each other. So we have to use parallelogram law and the law of sines. Also determine the orthogonal projection PA of R onto axis A. The orthogonal projection PA of R is the component of R in the direction of the A axis, which will be presented later here. So this is the figure. Then let's draw the force R and parallel to A and B to form a parallelogram as shown in the figure. So we have 800 newtons, then this is the B axis, the A axis, and the angle 110 and 30 degrees. Therefore, the total angle here is 110. One interior angle of the parallelogram is 110 plus 30, 140. Therefore, this other interior angle is 180 minus 140, so this is 40 degrees. These are the components RA and RB, which are all positive because in the direction of A and B. So again, this is RA also, parallel to that. This is 40 degrees. 180 minus quantity 110 plus 30. So this is 40 degrees. Property of parallelogram, 30 degrees. So this is also 30 degrees. Another way to compute that this is 30 degrees is 180 minus 110 minus 40. In a triangle, 180, the sum of interior angles, minus 110, so 70, minus 40, so 30 degrees. Or in other words, they are equal, transversal angle. So by law of sines, 800 as to sine 40 equals RA as to sine 110 equals RB as to sine 30. We can solve for RA and RB. So 800 newtons as to sine 40 equals RA as to sine 110 equals RB as to sine 30. RA therefore is 800 sine 110 divided by sine 40. So it is 1170 newtons. R sub B is 800 sine 30 divided by sine 40. So R sub B is 622.3 newtons. Then from the tip projection, orthogonal projection PA of R onto axis A, the component of R, 800, in the direction of A. So first we draw from the tip perpendicular to A axis. Then this component here is P sub A. What is that component in this right triangle? The hypotenuse is 800, the angle is 30, so that is PA 800 cosine of 30 adjacent to 30 degrees. So P sub A is 800 cosine of 30 degrees. So P sub A is 692.8 newtons. Level 15, this is the last. Determine the components FA and FB of the 4 kilonewton force along the oblique axis A and B. Determine the projections P sub A and P sub B of F onto the A and B axis. So this is the given figure. And first, for the components FA and FB, we draw lines through the tips parallel to A and B axis to form a parallelogram as shown in the figure. So parallel to B, parallel to A. So that's it. So this is FA and that is FB. For the angles, 90, this angle here, the measure of this angle is 90 minus 30 minus 40. So this is 20 degrees. 90 minus 30 minus 40, 20 degrees. This angle is 40 degrees minus 15 degrees, 25 degrees. So therefore, 20 plus 25, one interior angle of the parallelogram is 45. So this angle here is 180 minus 45, 135 degrees. And this angle and that angle must be equal, so 20 degrees also. Another way to compute 20 degrees is in this triangle, 180 minus 25 minus 135 is 20 degrees. So there are many ways to determine those angles. So by sine law, 4 kilonewtons, the red one, diagonal, as to sine 135 equals FA as to sine 20 equals FB as to sine 25. Opposite to FB, this one is 25, so sine 25. Therefore, FA is 4 sine 20 over sine 135, 1.935 kilonewtons. FB is 4 sine 25 degrees over sine 135, 2.391 kilonewtons. Then for the orthogonal components, so we draw from the tip of F perpendicular to A first. Then this is P sub A, that one. So notice that this is a right triangle and the angle is 25. Adjacent, this one is adjacent, so it is hypotenuse for cosine 25. So P sub A, orthogonal component of F onto A, is 4 cosine 25. So P sub A is 3.625 kilonewtons, while we draw line perpendicular to B first. Then this is P sub B. And this is a right triangle with angle 20 degrees, PB is adjacent, so it is 4 cosine of 20. P sub B is 4 cosine of 20 degrees. So P sub A is 3.759 kilonewtons. So that's it for this video. I hope that you were able to follow and you learned a lot, especially for computing components of a force, rectangular or non-rectangular components like this, tangential, normal. You need that in analyzing four systems, resultant of four systems, because you have to compute for the components. It's easy to compute the components, rectangular or non-rectangular, before we compute for the resultant of the system. So next video will be resultant of coplanar concurrent for systems, but we'll have so many techniques. We can present, I think, four, but we will not present the parallelogram law before in the first video because it is lengthy. We'll just apply components. It may be vector or the standard position of components so that we can compute the resultant in an easier manner, like also for this case here. So that's it. I hope that you enjoyed watching and you learn a lot. If you feel that my presentation is helpful in your studies and to your friends, please share it. Please share my video so that you can also help them and you also introduce my channel to them. That's it and bye bye.